I will talk about how we can generate our pictures better with a bit more understanding of how diffusion neural network works. Basically, what we just adding, we're adding more splashes to our pictures. We write a paper. We got best paper nomination in big conference in Europe, Gecko. I did it when I was in Meta, so I worked there partly for research for stable diffusion and diffusion models, how we can move them forward. Right now it's switch and I'm working in startup with Wizium.ai, but this will be correspond to my work to Meta, which we published, and it's open source, so if you're interested after that, I can share you links. You can go to GitHub, and it's all prepared to run from scratch in Google Colab, even if you don't have your own server to run a neural network. So let's start talking. I will start from first a bit technical background, if not everyone familiar with how diffusion model works. Then I explain what we actually introducing, what about how we're moving this forward, and the last I share some insights from the diffusion area which we learned from this research. So let's start the first part. I will start from the very beginning because I expect that everyone has different depths of knowledge. First of all, it's a very ancient story about UNet, which was developed, I think, roughly 10 or always 15 years ago. So, which is based on convolutional neural network. Convolutional neural network is just representing pixels, like the pixels that we have in normal image, to neural network to convolve some set of pixels to different space with providing more depth. What we're actually seeing here usually correspond to seeing some patterns. So convolutional neural network usually works. They have the set of these convolution layers which retrieve patterns from images to learn on these patterns rather than on pixel itself. So very simple approach, but it was the key stuff to move all image analysis and neural network forward about 12-15 years ago. And one of the stuff was UNet. You can see it here. So it's called U because it's like looks like a U letter. The main idea is using max pooling and convolution. Max pooling when we decrease in dimension of our image. We decrease in dimension first, and then trying to reconstruct image from the low dimension back, and have these residual connections on the same layers. Why it's so important? Because with this connection we can really do as a denoising, but also image segmentation to find some very important stuff in images on a low level. Originally, UNet was developed to make medical image segmentation to find some important part on the images. So it's the first part of technology that we're using. Second part of technology is attention. Is what our transformers based now, like all the LLMs based on transformer architecture, which based on attention, which was introduced in 2018 on very famous paper, Attention is All You Need. Let's make a very bold statement that attention is all you need, but it's actually coming truth, as right now transformer is using for particular everything. So the basic idea of attention is based on recursive neural network, which is described here is when we have any sequence. It can be letters, it can be pixels, any sequences. We just using output of a previous prediction to new prediction and call this RNN. And based on this, we build an attention mechanism, which maybe looks a bit complex, but main idea behind that is not really hard to understand, as we have additional fully connected layer. Here is red A01 and 02, which create a context vector which corresponds to areas of our sequence on which we wanted to make a special attention, why it's called attention, when we generate the next item in a sequence. So the main idea is, instead of do our prediction just as is, let's add some context vector which we generate with fully connection layer to make this prediction better, and it actually works. So based on attention, we combine this with UNet and make UNet with attention, which calls like actual a neural network which is very close to diffusion, what we have right now. So the main idea here that we have our UNet, as I mentioned before, but on our connection between layers, we also use attention mechanism, which means that when we're trying to reconstruct our picture from low-level design, we use attention mechanism to see on which part of the picture on corresponding layer we wanted to pay more attention. So this is UNet with attention is the core part of all diffusion process. So and the next step, we can go forward to talk about diffusion process itself. Diffusion process itself take some images, take some text, and generate output image. As a start, it takes no image, which means it can take some random noise and take some text and make a corresponding output images. Inside diffusion process, we have UNet and has multiple iterations. So we iterate new images, adding noise, using UNet again, with all this stuff generating new images, adding noise, using UNet again, generating new images, and like 50, 60 iteration will do that until output image wouldn't be perfect. And so if we trying to go inside, we can explain it in a bit more details. So we have our diffusion process, as I mentioned, from pixel space, then we do convolution, go to latent space, then we add in noise, mix up with the text. Text we also have to prepare to move text to latent space, to mix up with our image, go through the noise in UNet, then reconstruct the image to pixel space and do it again and again, as I mentioned. And all this part has their own name. So right now it's all very deep, and there are a bunch of papers how to do noisy latent vector better, how to do text image transformer better, how to do like every part, like slightly improvement on each part can be done. And what we've done investigation of the part when we combine text with the image, how we can improve our image that we generated without refitting, relearning, or fine-tuning our neural network. So we can do this just using neural network as it is, with manipulating constants of this process, rather than do refit or finding some data sets. So how we do that? Why all this math not really needed to do images better? Because the main idea behind of this all complex math is very simple. We just, like a painter, we bringing some colors, bring into the our picture, and then like a painter trying to use these colors to make pictures a bit more sustainable, a bit more reliable, and closer what we wanted to see. the idea is, what if we not just make a constant noise and bring colors everywhere, and we will just bring this color on particular part of the image what we wanted to change. And apparently, so spoiler, it will work. So in our image, when we add noise, we will add noise on not on all image, but on particular parts here. And then go to change this part of the image. Why it's so important to investigate this part of the process? Because the next step, we can suggest user to select the part of the image he wanted to change, and then change particularly the part of the image. And if we go into mix up this part of the image with embedded text, we allow user to generate not regenerate full picture, but regenerate part of the picture with especially object or change what user wanted to change. And this will be introduced to full picture organically because we add a noise there. So this was our idea. So we do that, as I mentioned, we do it in Meta, and advertisement is very important part, and usually people who do advertisement, they, for example, if you promote some product, I don't know, this stuff, you wanted to see it exactly as it is on a picture, not just something looks like that, as usual diffusion models doing. Something similar to, they wanted to do exactly what they wanted to, and this can be achieved only by iterative improvement, not with one go. Even with better neural network, I think everyone here use LLMs, and we all do know that it's hard to get perfect match with one shot. So there should be some iterative stuff, and what we're doing here, we're providing opportunity to do this iterative stuff. So the last, I think, math part here. Next will be pictures, I promise. There will be one more algorithm explanation, but math is the last one. So what if user will click and wanted to change different part of the image at once? For example, add something here, and remove from one place and get another place of the image as it is. So to do that, you can see user clicks here. We use Voronoi space splitting. So it's a very simple idea. For each pixel, we see the closest user click, what part of the image user selected, and based on that, we identify what user really wanted to do with this part of the image. Wanted to change it, wanted to keep it, or wanted to do something else. How it actually works. Let's go to pictures. For example, user generates some guy and spider near the modern building in a city, and it was stable diffusion generated for him, but user not satisfied with this paw of the spider, with this leg, somehow. And he wanted to change that, but everything else he wanted to keep as it is. So user makes a click here, and then what we're doing, we're trying to add noise around this part of the image and continue diffusion process, continue regeneration. And now what we get if we add different amount of noise. First of all, if we add very less noise, it's very less change here. Then when we start in adding more noise, it can change. You can see here this paw somehow disappeared. Here is also changed a bit. You can see even if you compare this one to this one, different bolts of that. We continue adding more noise, and it's like drawing new spider here somehow. We continue adding, and it's created a very big leg. And at the end, when we add a lot of noise, it's changing spider itself. But based on this point as well, because this is the center of the noise we're adding to the picture. So, and with manipulating this stuff, we we are providing user opportunities. Why it's so great as a result of this research? Because we can provide user different results of what he wanted to. For neural network, it's a big problem to understand what user really want to. When user does click here and say, I wanted to change, it's really hard, even for real people, for designer to understand what the customer really wants from him. But for neural network, it's almost impossible to understand what user really wanted to change. And here we can generate a bunch of images with different amount of changes to say, okay, now you can select. And another great stuff here is that we can generate it iteratively, so we no need to rerun it from scratch every time. We just generating it iteratively, so to build one based on another one. So the last, as I mentioned, about algorithm, how it works. So it's a classic diffusion process. As I mentioned, it do UNet roughly 50 times, creating new latent space based on that, then decoding to normal pixel space. And what we are doing, we adding our big part here to identify where to add noise, calculate Voronoi distance, based noise based on that, and get a result, but keeping the main cycle as it is. Why it's important? Because here we're not refitting neural network, we're not doing fine-tuning, we just adding one more step in diffusion process. It's become cheap, so you don't need a huge cluster to apply this. So another real-life stuff that you can see in examples in GitHub, what we provided, it's we have a red, we have a paw. I don't know why we're changing paw every time, but it's easy to demonstrate. So and then we can just change the paw. You can see the red itself, or it may be mouse, keep as a cheese, cheese keep as a cheese, roughly. But this part of the image changed completely. And the last part is, okay, what if we're not changing not only image itself, but the text as well? So what's the idea here? User first provide us a prompt. For example, here, I wanted to see the forest. Forest in summer with some road inside. But then, as usual customer, for every designer, user change his mind and say, okay, let's do this forest burn. And what we usually do if we're using neural network, we providing new prompt and say, let's try this forest burn, get new image. But in fact, as a usual designer, we don't know what does it mean for user. He wanted to forest first, burn forest at the end, but what's the really purpose? And what we're doing first point in latent space in text, what user has before, new point at latent space in text, what user has with the new prompt. Then we build in the line between these 2 points. And then we're generating not the image on the last point, the last user intention, but with different points on this line from the original one to the last one. And then we found the very interesting insight that in this latent space, when we starting going through there, it's not just some mess between. It's really we got in first we have some trees in a forest, then it's starting slowly burning. You can see less trees, less grasses. Then it's starting one fire. Then there's a lot of fires everywhere. And the user can choose how really he wanted to burn a forest. A bit or full forest burn, or just make less grasses and it's about to. The same here with the Paris. You can see the Paris at night and then Paris at night with lights. And also, when we starting a build from first to the last one, it's not something useless in between. It's also pictures which user can choose. And with this iteration, we can provide user more opportunity to choose appropriate. The last, what I also experimented, I generated forest in summer and forest in winter, and generated in between, and it really generates a forest in autumn with leaves starting falling, forest starting going to blue and red, and winter with ice at the end. So it's interesting outcome that user also can use as it's providing more ideas how to respect user prompts. So that is here. I don't know if slide will be shared. You can go to our paper. As I mentioned, we also publish open source our code in GitHub, in FAIR repo. This all co-authors of this paper. It wasn't only me who worked on that. Thank you for your attention. I think we have time for a couple of questions.
Yeah, definitely.
Yeah.
I don't know about diffusion models, but actually nothing. It will be a very stupid question. When you show the spider, and it has some problem with his leg, and do I understand right that user can click on the leg, and don't write something? There is no another prompt that please take away the leg. Is it expensive to, as I understand, well, you have stable diffusion, have the picture, then some part you want to correct it, and it is easier not to start with another prompt from the beginning, but just change this, just make one more step with some correction. But is it expensive to put text what I want to correct at this feature?
It compares the same computational expensive, because what we're actually doing when user selection lag, we added some noise and continue diffusion process. To continue diffusion process, we mix up our picture with text embedding. What this text embedding will look like is up to user. By default, we can use the old one. If user wanted to provide new one, we can use a new one as well. So, and in terms of computational speed, it will the same, so the only difference is transformer from text to text latent space, which is not very expensive. So user can provide, to answer a question, yes, user can provide what he exactly wanted to see there. I can add a bit more, so we make one research here to try to learn based on user clicks and providing text. If user working for so long with the picture, providing text and clicks, then we build in another predictive model to predict will user will be like this part of the image or not. But it will be another research, and you have to spend a really long time on this picture.
But with the example with the spider, there is no such text, because it's changed. Well, there are so many parents, and
no, there is no such text because we add a noise. Noise is some random stuff that we're adding, and some random stuff appearing from this noise.
And noise everywhere, not only this.
On this part of the picture first, and then a bit less around, a bit less around.
That's why it's so.
Yeah, it's the only way to keep other pictures sustainable and keep other picture as it is.
Okay.
Yeah. Yes. Yeah.
So you test if this works as well in different languages compared to English. Have you made tests now? Because I have a hypothesis that it may work a bit differently in French, in Russian, and another language.
Yeah, thank you. So we're working in diffusion process with text latent space representation. To make text latent space representation, the transformer is used. So, and the languages depends on how this transformer was fed. And what we're expecting that latent representation is like non-related to any languages. And if we're using some basic stuff from language, summer, forest, house, it's kind of the same in all languages. Of course, in different languages, the same word has different meanings, and it can be more complex, but we haven't go too deep there. So basically, we're using English or very simple construction on other languages. Yeah.
Thank you.
Yeah. Yes, yes.
Do you do any other experiments with latent representation? So let's say in the slide when you showed like how you interpolate between like forest and fire.
Yeah.
So like in the latent representation of this diffusion models, is there any algebra preserved? Because you remember like inside of the work vector, if you could like get the vector for a king and add vector to a woman, you get the queen. But for instance, in this example with the forest, fire, and Paris, if we would just subtract the vector from forest and fire, and add Paris into the Paris and fire.
Yeah, you can see.
So like if you do this kind of experiment, and the second thing, like not only the algebraic structure, but like logical structure. So you're saying that you interpolate between the Paris in summer and the Paris in winter. You said that it shows the Paris in autumn, but why not the Paris in spring? So like does it preserve this like cyclical structure inside of it, or is it interpolation is just linear? Like did you do something like that?
Yeah. I think it's a great question. So it's a part of that we played a lot on this case. So linear algebra is really simple. We have just multi-dimensional space, 2 points, and build a line between it, and taking point on the line. And it really depends. For example, we tried like cat in the room and room without cat, and it doesn't show now like half of the cat, or I don't know, cat with standing and going outside. It does transforming cat with something with stuff, small, and then it disappeared. So why not? If you say why not Paris is spring, when forest is spring? I think because autumn is for diffusion is easy to show, because autumn is more like, the color is very specific, and it has more signs to see, rather than Paris in spring. Maybe it's tried, but we not recognize this is spring and that's the normal summer or normal Paris. I don't know. But autumn we recognize easily, and the same here with fires or lights. It really depends, I think, on the meanings of the text. That do the meanings that we're operating with has different conditions? Can we multiply this meaning to something? If we do, we can see the result. If we're not, we can see some maybe weird result, but it's still, like, I think from user perspective, and can still kind of relevant, because it will generate picture which somehow related what he wanted to, and he has the opportunity to choose. Not just writing, do the same but other, do the same but better, do the same but more than what I wanted to see. So in this case, we're somehow trying to operate with that.
Thank you.
Thank you.